So I'm very happy to talk about the cosmological collider physics and how we can use it to probe extra dimensional scenarios, focusing specifically on the case of warped extra dimensions. So needless to say, we are in the era of precision cosmology. We have measured the anisotropies on the CMB sky and inhomogeneities in large-scale structure pretty well. And one thing you can say by looking at all these fluctuations is you can wonder where are they coming from? What kind of primordial physics could give rise to these fluctuations? And the leading candidate that we have to explain these is cosmic inflation. The idea is that when the universe was very, very young, there was an epoch when the universe expanded very rapidly in an accelerated fashion. And during this epoch, small scale quantum mechanical fluctuations, they got stretched to very, very large sizes and eventually sourced the anisotropies that we see on the CMB and inhomogeneities on the large scale structure. So this is a very exciting idea. However, there are lots of things that we do not know about cosmic inflation, including the energy scale of inflation, what kind of physics drives inflation, how it ends, and from a microscopic side, we do not know what kind of particles or fields or states were active during inflation. So in this talk, I'm going to focus on this very last question. Now, in general, this is a pretty broad and open-ended question. One way of thinking about this is to compare the masses of potential new states with the Hubble scale during inflation. So if the masses are much, much smaller than the Hubble scale, then just from the space-time expansion, lots of these particles would be produced. And if they are long-lived, they can, for example, survive as isocurvature fluctuations and impact CMB anisotropies. There are many examples of this, including dark matter isocurvature. And in a recent work with an amazing group of collaborators, I have also explored what would happen if these new particles survive today as dark radiation and how dark radiation isocurvature can impact, for example, the CMB anisotropies along with other observables. So here is, for example, a quick summary plot showing the constraints from the current data. You can also think about very, very heavy particles whose masses are much, much larger than the inflationary Hubble scale. Because their masses are so large, they are produced very rarely. But if there are coupling to the inflaton field, then these particles, they can basically create a drag force on the inflaton and modify or deform the space-time metric in a very, very localized fashion. So you basically have a bunch of localized overdensities that can give rise to hot or cold spots on the CMB, and it can also give rise to high redshift rare galaxies. So here is, for example, a quick snapshot. This is a mock CMB map, and here are, for example, a couple of hotspots coming from this very heavy particle production. In these papers, we have outlined some of the detection strategies and carried out a search using Planck data to look for these kind of hotspots. And although we did not find anything, we are able to set some interesting constraints. Here is how these localized overdensities, how they can affect structure, for example. So here is a seed caused by a very heavy particle that can, for example, eventually evolve to a rare galaxy at very high redshift. This is just, again, a simulation coming, an n-body simulation snapshot that we are currently working on. So in this talk, I'm not going to talk about either of these two possibilities, although I'm very happy to chat about this during the discussion session. But I'm going to focus on the possibility when these particle masses are close to the Hubble scale. And the cool thing about this is that they can be naturally produced during inflation without any type of special coupling. And they can give rise to different types of signatures in the correlation functions. For example, the power spectrum or 3 or 4-point correlation function via primordial non-Gaussianity. So let me quickly explain the physics associated with Hubble scale particles during inflation. Since the rate of expansion of space-time is Hubble, these particles, they're just naturally gravitationally produced without any extra ingredient. Here is one such event where you have a pair production of these particles. So here is one particle with momenta ki. Here is another one also with momenta ki. And you can show that this production event would typically happen around a conformal time of 1 over ki. Roughly speaking, this is the time when the size of the mode becomes comparable to the horizon size, and the mode realizes that it's no longer in flat space-time, but rather it's in some expanding space-time. And after a while, these particles, they can propagate, and if there's a coupling to the inflaton, they can decay into a pair of inflaton fluctuations each. So denoting the momentum of these legs as k1 through k4, what you would predict is that there is a non-trivial 4-point correlation function of inflaton fluctuations, and by momentum conservation, these 4 momenta, they form a quadrilateral. Now, there is one interesting configuration of this quadrilateral, the so-called collapsed shape, which is when the vector sum of 2 of the external momenta is much, much smaller than any of the external sides. So it's like collapsing the quadrilateral. So interestingly, what happens in this limit is you can show that given this value of ki, while the production time is given by 1 over ki, the decay time of this particle, based on just local energy conservation, is actually given by the size of the external momentum. So for example, 1 over k4. So since ki is much, much smaller than any of these external momenta, this basically means that between the production time and the decay time, there's a long gap. And what that means is that within this time window, the heavy particle, it gets produced and it propagates on shell during this time window. And one thing that we know from quantum mechanics is any massive particle propagation, you can describe it by some factor of e to the imt. So this is basically the time difference between the production and the decay. And if you express this cosmic time in terms of conformal time, and then use this relation between the momenta and conformal time, you can show that this kind of process would have some sort of non-analytic momentum dependence of this kind. And if you write it in a more legible form, you basically would guess that there is a cosine dependence of this 4-point function, where you have the cosine of the log of ki over k4, and the frequency of the oscillation is given by the mass of the heavy particle. Okay. So more precisely, if you do it, you would find that indeed there is this cosine log dependence, and the associated frequencies indeed given by the mass of the heavy particle, with the usual 9 over 4 factor comes in because we are in quasi-de Sitter space. But then interestingly, if this particle has some non-trivial spin, you would also expect a non-trivial angular dependence of this trispectrum or the 4-point function. So here, for example, the angle dependence would come in, and the angle dependence would be in the form of like θ1, θ3, which are the angles defined as here. And also it would depend on the dihedral angle, which is basically the angle containing between the plane containing k1 and k2 and k3 and k4. Okay? So the exciting aspect of all of this is that if we find a pattern like this in the trispectrum using data, then in principle from the oscillation frequency, we can extract the mass of the particle. And then from the angular dependence, we can potentially extract the spin of this particle. So you are effectively doing on-shell mass spin spectroscopy by studying this trispectrum. And this idea can also be repeated using the bispectrum or the 3-point function. And the interesting aspect of all of this is that these particles, they're as heavy as the Hubble scale, and the Hubble scale can be as large as 10 to the 13 GeV. So in principle, you are doing this on-shell mass spin spectroscopy of extremely heavy particles that you cannot produce in terrestrial or astrophysical settings. So the primordial universe is basically providing us with a very high energy collider, and hence the name Cosmological Collider, which was coined in this paper, along with this foundational work given here. And I should mention that along with these two papers, there are many, many interesting papers on this subject, but I'm not able to cite all of those references, but I'm happy to chat much more about these ideas and the history during the discussion session. So in the literature, a lot of people have thought about what kind of signatures would be there if you have, for example, scalars or fermions or gauge bosons as the massive particle. But rather, what we are going to talk now about is what would happen if you have a spin 2 particle in the intermediate line. For example, how would you model the spin 2 particle using quantum field theory rules? How large are the non-Gaussianity signatures? Are those observable using current or upcoming data set? Now, one robust way in which spin 2 particles can arise in field theory is if you have, for example, some strong coupling dynamics, something like QCD, for example. So you could have, for example, this strong sector active during inflation, and maybe upon confinement, it produces some spin 2. Now, in general, it is difficult to deal with strongly coupled theories, but there are certain limits where you can use other tools, for example, ADS-CFT, to make progress. And that is what we are going to do in this talk. So using ADS-CFT, the spin 2 resonance in a 4D strongly coupled theory, they're dual to Kaluza-Klein gravitons in a 5D theory. So what we are going to do is to study inflation in a 5-dimensional setting and understand the non-Gaussianities mediated by these KK gravitons. So to do that, let me quickly illustrate the setup that we'll have in mind. So we'll consider a situation with a warped extra dimension where the space-time is basically just a slice of a 5-dimensional anti-de Sitter space, which is bounded by the UV and an IR boundary. So this is the 5th dimension, and these are the transverse dimensions. They are the 4-dimensional slices. This, you can write the space-time metric as something like this. So this is the warp factor. A of t is the standard scale factor. Now, in the absence of any type of back reaction, the warp factor is just given by n of y equals exponential of minus ky, where k is the ADS curvature scale. In this talk, we are also going to focus on scenario where the size of the extra dimension is not going to change with time. So if you're familiar, this basically means that the radion field, which is associated with the size of the extra dimension, it roughly remains static as inflation happens. But it is possible to consider variations of this idea. Now, one irreducible aspect of this extra-dimensional space-time is that you, of course, have gravitational fluctuations. In particular, you will have around some static background, you will have some graviton fluctuations. And then once you do the standard extra-dimensional analysis, you will find that there is a graviton zero mode that is localized on the UV boundary, and any states that are there that talk to this graviton zero mode, which is responsible for reproducing 4D gravity, all those couplings would be suppressed by the Planck scale. Okay? However, excitingly, there are also KK graviton modes, which are localized on the IR boundary. And any field that is on the IR boundary, its coupling to the KK graviton modes, they're not suppressed by the Planck scale, but rather, in general, a smaller scale lambda. That is, if you want, it's some warped down Planck scale. So since the couplings are less suppressed compared to coupling to the graviton zero mode, you would expect that these kind of anything that, like, for example, KK graviton inflaton coupling, that can potentially give rise to much larger signatures at the cosmological collider, just from the fact that you have a smaller than M Planck suppression. So let us now discuss how to implement inflation in this setting. So one simple possibility is that you can first think about is maybe the inflaton field is something that is localized on the UV boundary. But then I just told you that because the KK graviton mode is peaked towards the IR boundary, this coupling would be Planck suppressed. So inflaton KK graviton coupling would be Planck suppressed. And as a result, this would give rise to pretty small non-Gaussianity. This is sort of similar to what happens in flat extra-dimensional scenarios that we studied a while ago. We found that the FNL parameter, which is something that is used to quantify the strength of the 3-point function, it's pretty small. It is still potentially detectable within future instruments, especially those using 21 centimeter experiments. So you can try putting the inflaton on the IR boundary instead. And in that case, what you would actually find that there is a stronger coupling now between the KK graviton and the inflaton. However, since the inflaton is there, you should also have enough energy in the inflaton field to drive inflation. However, to have a consistent description, you would like the inflaton energy density to be smaller than the IR scale, which is given by lambda. This is in general fine, except it just says that the IR scale is now much bigger than the Hubble scale. And that just means that all the states associated with extra dimension, including the KK gravitons, they are very heavy, so you cannot produce them on shell. And the oscillatory non-Gaussianity that I was talking about, they will be very suppressed. So there is a way out of this, which is to invoke a second field in spirit that would be, for example, the very well-known curvaton field. So if you have a situation where the curvaton field is on the IR and the inflaton is on the UV, then the story would actually go through pretty nicely. So in this case, the inflaton can drive inflation and its potential energy density can be, for example, much smaller than the Brent tension or the boundary cosmological constant. So you can have a controlled setup. And since the curvaton does not have to drive inflation, its energy density can be much smaller. It can be much smaller, for example, the IR scale. And once again, you can have a controlled description. And finally, because the curvaton is on the IR boundary, it does overlap significantly with the KK gravitons. So you do get a stronger coupling, which eventually would give rise to much easily observable non-Gaussianities. So as a very quick review, how the curvaton cosmology would work. So the standard idea is that during inflation, you have the inflaton energy density, then inflaton decays, inflation ends, and you have some dilution. The curvaton field, on the other hand, it has a much subdominant energy density during inflation, but eventually it comes to dominate the energy density before decaying and giving back the standard lambda CDM evolution. But because curvaton eventually dominates the energy density, you can have a situation where all the density perturbations that we are observing, they are basically coming from curvaton fluctuation. So now we can actually compute this KK graviton curvaton couplings and what kind of non-Gaussianity we can get out of this. As one technical aside, you also have to stabilize the extra dimension, and this can be done using the familiar Goldberger-Weiss mechanism, which we do discuss in detail in our paper, like how to, for example, solve for the Goldberger-Weiss profile, what is the back-reacted warp factor. So all of these details are in here if you want to have a look. So let me now get to the result. So here, for example, so I've been talking about KK gravitons, but then there is also another irreducible gravitational degree of freedom, which is the radion. This basically corresponds to the size of the extra dimension, and it's basically the fluctuation of the radius of the extra dimension, if you want. So that's the radion mode. You can parameterize in, for example, in this way, where the radius is basically an x-dependent quantity. So that's the field. And then using standard techniques, you can compute, for example, the coupling of the radion with the curvaton and the coupling of the KK graviton with the curvaton. And once you do that, then you can compute, for example, what kind of 4-point function the radion mediates. And here is, for example, the associated strength of the non-Gaussianity, which is conventionally parameterized by the tau NL parameter. So we find tau NLs, which are of the order of 10 to the 5 or 10 to the 6, depending on the benchmarks. And here is, for example, the current bounds on the tau NL. So especially for benchmark 2, it's kind of comparable to the current bounds. So it would be useful to do a dedicated search of these signals. You can also do the same thing with KK gravitons being the intermediate particle. And here you actually do get interesting angular dependence as useful or as relevant for a spin 2 particle. And here are the associated tau NLs. In this case, these values are a bit smaller than the current bounds, but with future data, we can potentially probe these types of non-Gaussianities. So here is my last slide. So just to end, inflation, we are going to have lots of interesting probes that can tell us about the physics of inflation. In this context, the Cosmological Collider is a very promising probe. It can let us do mass spin spectroscopy at very, very high energies. We have studied how we can use these ideas to probe warped extra dimensions, but there are lots of other concrete particle physics models that you can test using this. And interestingly, you can carry out some of these searches with CMB and large-scale structure data. So with that, let me end here, and I hope to discuss more during the discussion sessions. Thank you.